All right, let's talk about something that you use every single second but probably never think about: how the internet doesn't just collapse. We're going to pull back the curtain on the incredible engineering that manages a mind-boggling amount of traffic every moment of every day.
I mean, have you ever really stopped to think about that? Billions of people searching, sending emails, watching videos, all at the same time. How on earth does a single company handle that absolute fire hose of data and still give you an answer in like a fraction of a second? Well, the answer is a brilliant piece of engineering that's basically the internet's ultimate traffic cop.
So it all comes down to this one big idea: load balancing. It's pretty simple, really. Look on the left. If you send every single request to one server, it's going to get overwhelmed and just fall over. It becomes a single point of failure. But on the right, you see the solution. You get a whole team of servers, and you just share the work. This simple idea of sharing the load is what makes the whole modern internet even possible.
But, for a company the size of Google, this isn't just some textbook problem. It's an engineering challenge on a planetary scale. The sheer volume of traffic they deal with meant they had to invent a completely new way of doing things.
And this slide just nails that shift in thinking. On the left, that's the old school way. Giant, super expensive, specialized hardware boxes. They were inflexible, they couldn't grow as fast as Google was growing, and they only offered this basic 1+1 backup. If one died, another one took over. Kind of clumsy. On the right, that's the Google way. It's not one big box, it's a huge fleet of normal, everyday servers, all running some incredibly smart software.
And that's smart software. Well, it's got a name. This is the hero of our story: Maglev. It's Google's custom-built, software-based answer that completely blew the old hardware solutions out of the water.
This quote from the original research paper tells you everything you need to know. The keywords here are distributed software system and commodity Linux servers. This is a huge deal. It means Google isn't using some exotic, million-dollar piece of hardware. Nope, they're using the same kind of standard, off-the-shelf servers they use everywhere else, but they're running software that makes them more powerful than any specialized box could ever be.
Okay, so let's trace a request and see how this actually works. Your request comes in from the internet, it hits a router, and that router uses a technique that's basically a fancy way of saying it just sprays the incoming data packets evenly across a whole pool of these maglev machines. Then, whichever maglev machine gets your packet intelligently picks the right backend server, they call it a service endpoint, to actually handle your request, and it forwards the packet on.
But here's where it gets really clever. Think about it. Your incoming request, like a search query, is tiny, just a few bytes. The response, though, the whole search results page with images and everything, is way, way bigger. So maglev only handles the tiny incoming packets. The huge response is sent directly from that service endpoint straight back to you, completely bypassing maglev. This trick is called direct server return, and it's brilliant because it keeps maglev from ever becoming a bottleneck.
So what's the magic here? How does maglev pull off this incredible performance? It really boils down to two core, game-changing ideas. This is the secret sauce.
First up, speed. To get the insane speeds they needed, maglev does something that sounds a little wild. It completely ignores the main operating system. The standard networking software built into Linux is great, but for this one job, it's just too slow, too much overhead. So maglev talks directly to the network hardware, grabbing packets right off the wire and processing them itself. It's kind of like hot wiring a car for maximum performance.
The second big idea is all about stability. You got to remember, in a data center as big as Google's, servers are constantly being taken down for maintenance, or they fail, or new ones are added. Now, if a server disappears, you don't want to just randomly reshuffle all the traffic, because that would break millions of active connections. The solution is a really smart algorithm called consistent hashing.
And this table shows you that magic in action. So before, you can see connections are spread out across 3 servers: B0, B1, and B2. Now, look at the after column. We've just removed server B1. Instead of total chaos, look what happens. Only the connections that had to move, the ones that were going to B1, get a new assignment. Everything else, all those other connections, stay exactly where they were. That is how you get stability at an unbelievable scale.
So, okay, we've got these two super clever ideas, bypassing the operating system for speed and consistent hashing for stability. But what does that actually get you in the real world? How fast is fast?
Whoa, the results are just staggering. This chart says it all. The blue bars, that's the performance using the standard Linux networking. The orange bars,
That's maglev, with its kernel bypass trick. It's not even a competition. With just a few CPU cores, maglev's performance just explodes, and it can easily max out a 10 gigabit per second network connection.
And that all leads to this incredible number. At its peak, a single maglev machine, again, running on a standard, boring server, can process over 12 million data packets every single second. That level of efficiency is just mind-blowing, and it's what allows Google to operate at the scale that they do.
Now this is where the story gets really interesting for all of us. This amazing piece of internal tech, which was born out of necessity for Google to solve its own massive problems, didn't stay locked away in a vault. It actually became the foundation for products that anyone can use.
That's right. The exact same battle-tested, high-performance maglev technology is what's running under the hood of Google Cloud's public load balancers. So when developers are building their own apps on GCP, they are literally standing on the shoulders of this decade-long engineering giant.
So what this means is that developers now have this incredibly powerful toolkit. But, of course, with all that power, you've got to know which tool to pick for the right job.
And here's a super simple guide. If you're dealing with web traffic, HTTP, the application load balancer is your best friend. It's smart about things like URLs. For more general TCP traffic, you'd probably use the proxy network load balancer. And for absolute top-tier performance, think online gaming with UDP traffic, the pass-through network load balancer is what you want, because it's the fastest and even keeps the original client IP. They're all different flavors of maglev, each one perfectly tuned for a specific task.
You know, the story of maglev is such a powerful example of this massive trend where software is just eating specialized, expensive hardware for lunch. It proves that with really clever algorithms and smart systems design, you can get world-class performance out of regular commodity machines. And it just leaves us with this one big question, right? What's the next big piece of physical infrastructure that's about to be made obsolete by an even smarter piece of software?